Whether you're standing on the massive granite peaks of Yosemite or staring out at the black basalt plains of Hawaii, every single igneous rock tells a story of exactly how it was born. And to read that story, we just need to understand one master key. We call it the igneous silica spectrum.
So, here is our roadmap for the explainer. First up, we've got felsic, the silica heavyweights. Then we'll move into intermediate, the middle ground. After that, mafic, the dark side. And finally, ultramafic, deep mantle secrets. Let's get into it.
Okay, so the fundamental rule of igneous rocks is actually pretty straightforward. It boils down to this. Mineral composition, combined with the cooling environment, completely dictates every single rock type. If you look at how these are systematically mapped out, the top classifications give us our extrusive and intrusive rock names, things like rhyolite and granite. And then, beneath that, we see exactly which specific minerals make up those rocks. Basically, if you know the minerals, you know the rock. It's like a giant geological puzzle.
But you might be wondering, what's actually driving this whole classification system? Well, it's silica, or SiO2. Silica is the absolute master variable here. It's the principal oxide constituent in magmas. Think of silica kind of like a geological glue. It polymerizes melts, and what that means is it links up to form these complex, really sticky networks. So the amount of silica heavily dictates the magma's viscosity, which is just how thick and gooey it is. But it also controls the temperature and ultimately whether a volcano is going to gently ooze lava or violently explode. Section 1. Felsic, the silica heavyweights.
When we call these melts silica heavyweights, we absolutely mean it. Felsic magmas are packed with greater than 65% silica. Honestly, some even push past 70 or 75%. Because of this massive amount of silica, these melts are incredibly polymerized. They are highly viscous, super gooey, and because they're so thick, they trap expanding gases. This is exactly why felsic magmas are responsible for the most catastrophic volcanic eruptions in Earth's history. We're talking about those massive caldera-forming blasts at places like Yellowstone.
Now, where does the name actually come from? Well, felsic is a really clever mnemonic adjective. It's derived directly from the words feldspar and silica, so the name itself acts as a built-in cheat sheet for its mineral makeup. Which brings us to exactly what's inside them. Felsic rocks are absolutely dominated by quartz, usually making up about 25 to 35% of the rock, alongside abundant potassium feldspar, often called K-spar, and sodium-rich plagioclase, like albite. You might find some minor specks of muscovite or biotite mica in there too, but overwhelmingly, it's these light-colored silicates that give felsic rocks their characteristic pink, white, or light gray appearance.
Let's apply our rule of cooling environments to these felsic minerals. If a felsic magma gets trapped deep underground and cools really slowly, it has time to grow large, visible crystals. That creates the coarse-grained, intrusive rock we know as granite. But if that exact same magma erupts onto the surface and cools rapidly, it forms the fine-grained, extrusive rock rhyolite. So it's the exact same chemical composition, just radically different textures based on where it cooled.
Moving right along to Section 2, Intermediate, the middle ground.
In this intermediate category, the silica threshold drops down to between 52 and 66%. This moderate level is essentially the perfect geological compromise. It beautifully balances viscosity and temperature, so the magma is thinner than a highly viscous felsic rhyolite, but it's still sticky enough to trap gases and build up immense pressure over time. Mineralogically speaking, we're looking at a roughly equal mix of light and dark minerals here. Notice how the plagioclase feldspar shifts from being sodium-rich to a mix of sodium and calcium. We also get an influx of dark amphibole, specifically hornblende, with very minimal to literally no quartz. Visually, this 50-50 mix of light and dark minerals is what gives intermediate rocks a highly distinctive, classic salt and pepper texture. Once again, the cooling environment totally dictates the final rock. Slow cooling underground gives us intrusive diorite. That's your classic coarse salt and pepper rock. Fast cooling on the surface gives us extrusive andesite. What's super fascinating here is that intermediate magmas frequently form those highly explosive, steep-sided composite volcanoes that we see along convergent plate boundaries. In fact, andesite is literally named after the Andes Mountains in South America, which is a massive subduction zone. All right, let's turn up the heat. Section 3, mafic, the dark side. Down here, we see a significant drop in silica, plummeting to between 45 and 52%. With far less silica available to polymerize the melt, mafic magmas completely lose that sticky viscosity. Instead, they erupt at incredibly high temperatures, often well over 1,000 degrees Celsius. This creates highly fluid, really fast-moving lava rivers, exactly like the ones we constantly observe erupting in Hawaii.
Just like felsic, the word mafic is a portmanteau designed to be a clever cheat sheet for its chemistry. It combines magnesium and ferric, which refers to iron. So, whenever you hear the word mafic, you should instantly logically connect that name to a heavy iron and magnesium-rich chemistry. Because it's packed with all that iron and magnesium, the dominant ferromagnesian minerals here are dark and heavy. Mafic rocks are defined by calcium-rich plagioclase, things like labradorite or bitonite, and clinopyroxene, like augite, alongside minor amounts of olivine. And the really crucial thing to note here, zero quartz, absolutely none. The high density of these ferromagnesian minerals is what gives mafic rocks their signature dark gray and black colors.
Following our cooling rule again, if this dark magma cools slowly in a deep underground magma chamber, it forms intrusive gabbro. And gabbro actually makes up a massive component of the lower oceanic crust. If it erupts and cools quickly on the seafloor or at a hotspot, it forms extrusive basalt. Basalt is famous for creating massive, highly fluid effusive flows at mid-ocean ridges. In fact, practically the entire ocean floor is paved with basalt.
Finally, we are going deep. Section 4, Ultramafic, Deep Mantle Secrets.
Here we hit rock-bottom silica levels, coming in at less than 45%. But as the silica bottoms out, the magnesium absolutely spikes. Ultramafic rocks boast extremely high magnesium oxide contents, often over 18%. We are talking about the heaviest, densest, and hottest melts in the entire geological record. When we look at the mineral breakdown, this category is defined by a near-total dominance of heavy, green ferromagnesian minerals. They can be over 90% phosphatic olivine, mixed with pyroxene, and feature little to absolutely no feldspar whatsoever. Now, because these minerals form at the extreme pressures and temperatures of the Earth's mantle, they are highly unstable at the Earth's surface. If they get exposed to our atmosphere and water, they rapidly alter or weather away. The classic intrusive ultramafic rock is called peridotite, which is literally what the Earth's upper mantle is made of. Its extrusive equivalent is a rock called kommatite. But here is a truly amazing fact. Kommatite is incredibly rare on the surface of the Earth today. Why? Because our modern Earth has simply cooled down too much. Kommatite lavas required superheated eruption temperatures of up to 1,600 degrees Celsius. That means they flowed turbulently almost exclusively during the ancient Archean era, which was over 2.5 billion years ago. So bringing it all together, let's aggregate our entire journey into this ultimate cheat sheet matrix. Look at how perfectly these relationships align. As silica drops from felsic down to ultramafic, the eruption temperature goes from low to absolutely extreme. Conversely, the viscosity goes from being highly sticky in felsic rocks all the way down to incredibly fluid and watery in ultramafic rocks. And of course, the color systematically shifts from light to dark as iron and magnesium replace the silica. It's a beautifully systematic spectrum, isn't it? To wrap up, I want to leave you with a provocative thought. Now that you're armed with this petrology knowledge, let's look out into the cosmos. Imagine a rover on a distant planet discovers vast plains of basalts cut by isolated channels of comatite. What would that reveal about that planet's thermal history? Well, knowing what we now know about comatites requiring extreme, superheated mantle conditions, we would immediately know that planet was once violently, blisteringly hot, way hotter than Earth is today. That is the true power of the silica spectrum. You aren't just memorizing rock names, you are reading the thermal diaries of entire planets. Thank you so much for joining me on this explainer, and keep looking closely at the rocks beneath your feet.